In this recording, we're going to take a look at the manner in which the rate and depth of breathing are controlled. What you have in front of you is a picture of the brainstem, and in this picture of the brainstem, you see four distinctive areas that are identified. We're going to start near the bottom of the picture and talk about the medullary remissivity area first here. The medullary remissivity area is where most control of breathing / ventilation is going to originate. Within the medulla oblongata, you'll find this medullary remissivity area, and it's composed of two distinctive components. There's the inspiratory area and also the expiratory area. If you look at the inspiratory area, it is going to be utilized during your normal quiet breathing, and that's the only area you need it. However, during forceful breathing, in order to do a forceful exhalation, the expiratory area will be utilized. So let's just first discuss normal quiet breathing. When you normally breathe, the inspiratory area will activate for about 2 seconds. This is enough time for a message to be sent to the diaphragm and external intercostals, causing them to contract, and you get a normal quiet inhalation. In order to exhale normally, all that's necessary is for that inspiratory area to go inactive. That occurs for about 3 seconds. After that inspiratory area is inactive, the diaphragm, external intercostals, and the chest wall and lungs all utilize elastic recoil, and that recoil will lead to a quiet exhalation. So the take-home point is that when you normally breathe, you only use the inspiratory area. When the inspiratory area activates, you'll inhale, and when it goes inactive, you will ultimately exhale. However, in order to accomplish a forceful exhalation, what happens is the inspiratory area activates for a little bit longer. This usually leads to a deeper inhalation because the accessory muscles of inhalation, like the sternocleidomastoid and scalene muscles, will activate. At the same time that those muscles are activated, the inspiratory area also will activate the expiratory area. And after the deep inhalation is accomplished, the expiratory area will activate the internal intercostals and the muscles of the abdominal wall. And when these contract, it leads to a forceful exhalation. So, during a forceful exhalation, the expiratory area will be active, and it activates in response to a signal it receives from the inspiratory area, which is why the two, a forceful inhalation and also a forceful exhalation, are essentially yoked together. The next two areas are seen a little bit higher up in the pons and also the midbrain. They are called the apneustic area and also the pneumotaxic area. The apneustic area, the root of apneustic is apnea. So this is an area that activates when you stop breathing. When you stop breathing, the partial pressure of carbon dioxide will begin to rise. That will trigger the apneustic area to activate, and the apneustic area will send a signal to the inspiratory area, forcing it to go active. When the inspiratory area is active, remember, you will be made to inhale. So if you have children or kids and they say, oh, I'm going to hold my breath until I pass out or something like that, basically you can't do it, because as that PCO2 increases, the apneustic area would eventually activate. That activation will lead to activation of the inspiratory area, and you will be forced to inhale. Essentially, this is also the mechanism that plays out when people unfortunately drown. They would be holding their breath under the water. However, as the PCO2 increased, the apneustic area would in turn activate the inspiratory area, forcing inhalation. And finally, we have the pneumotaxic area. The pneumotaxic area ultimately has control over all those areas above it. Pneumo refers to air. Taxic, root, is in toxic. So what happens is, as the stretch on the lungs becomes greater and greater due to inhalation, the pneumotaxic area receives signals about that stretch. If the stretch becomes too great, maybe leading to a possible rupturing of the lungs, the pneumotaxic area will activate and shut down the apneustic and also the inspiratory areas. And once the apneustic and inspiratory areas are deactivated, you no longer have the ability to send a signal to keep inhaling. If you can't inhale any further, recoil takes over and you exhale, therefore preventing overinflation of the lungs. So these are the controlling areas of ventilation and depth of ventilation, once again located all within the brainstem. We won't discuss any of the reflexes, so we'll very quickly just discuss what primarily drives our desire to breathe or ventilate, and that is the partial pressure of carbon dioxide. The partial pressure of carbon dioxide, as it increases, will activate chemoreceptors located in the medulla that communicate with the inspiratory area, and also chemoreceptors within the aortic and carotid bodies. Once the message is received to activate the inspiratory area, that person will be forced to inhale, but in order to eliminate the carbon dioxide, they are also forced to exhale once the inhalation is achieved. Once that exhalation is achieved, you will begin to see a lower PCO2, and therefore all the benefits that come along with that additional ventilation, like a increase in the pH should the pH become too acidic, or an increase in PO2 would accompany as well. I do want to define for you very quickly also two terms, hypoventilation and hyperventilation. Hypoventilation is a lower than usual breathing rate. Hyperventilation is a faster than usual ventilation rate. So you should be familiar with those two terms and what they refer to as well. And with that being said, we'll kind of wrap up the discussion here about control of ventilation.